Hello, my amazing students. This is Mrs. A. We are working on 9.8. And 9.8 is talking about complex numbers. And I found a little bit bigger board, so maybe this will help us a little bit. Maybe it's too big. All right, so the first thing we're going to do is talk about the definition of I. And I is the imaginary unit. So we are starting to talk about complex numbers. And in the past, I've told you that when we had something like the square root of -1, we would have to say, that's not a real number, because there's no real number that I could square and get a negative, which is true. However, we have a whole bunch of applications that require the use of an imaginary number, okay? In other words, we would find problems that had the square root of -1 over and over in real life, okay? So some of the applications that we might find these complex or imaginary numbers in would be your electricity. Circuits involving electricity, the math behind those circuits would involve imaginary numbers. Heat mechanics, wave mechanics, light, any energy type of a function is liable to have imaginary numbers in it. So they do exist, and we really do use them. So we have to learn about them. So now we're going to define this imaginary unit I as the square root of -1. And we have an entire system of math designed to deal with these numbers. And for the most part, the complex math system is the same as the real number system, with a few exceptions, okay? So first of all, we're going to talk about what is a complex number. A complex number is a number of the form A plus BI, okay, where A is the real number part, the real number that we've been dealing with all the time, and then BI is the imaginary part. So B is the coefficient of the imaginary part of the number. The complex number has both real and imaginary parts. The complex number set, therefore, is going to include all real and imaginary numbers. Okay, and so one of the ways that we're going to learn to deal with imaginary numbers, complex numbers, is to always take the I out before I proceed with any kind of operation, okay? So I want to go ahead and simplify down to where I have my I pulled out, and we'll show you how to do that here. Okay, so we have the square root of -4, and we are supposed to simplify these numbers. The square root of -4 is the same thing as the square root of -1 times the square root of 4. Well, the square root of 4 is still 2. Okay, and then the square root of -1 we have defined as I. So we end up with I times 2, but we would usually write our I behind our 2. So 2I is the simplified form. And if we were going to write it officially in its complex form, it would be 0 plus 2I. But putting 0 plus is kind of tedious. So 2I is usually considered fine. Okay, it's the imaginary part, so 2I is fine. All right, so now we've got the square root of a -54, which 4 was a perfect square, but 54 is not a perfect square. So I'm going to split this up 3 ways. I'm going to split it up into a -1, and a -9, a positive 9, and a 6, because 9 times 6 is 54. And remember, I'm always trying to find a radical that has the biggest perfect square that I can find in it. So now the square root of 9 is 3. The square root of 6 is as simplified as I can get it. And the square root of negative 1 is I. Now the proper place for the I in this problem is going to be right here after the 3. I would never put the I on the other side of the radical, remember, because of the confusion about whether the I is inside or outside the radical. So we always allow our radical to be the last thing, and we will put the I right in front of it because the I is not under the radical anymore. The radical negative 1 is the I. Okay, let's look at the last one. The last one is a prime number, 11. So we're just going to break it up into the square root of negative 1, the square root of 11, and the answer is going to be I square root of 11, because the square root of 11 does not simplify any further. All right, so now we have some problems. We're going to start with, how do we multiply imaginary numbers? Now, when you're looking at this, these are two complex numbers or imaginary numbers. And if I were to use my normal product rule, then I could write this as the square root of 36, because a negative times a negative is a positive. And I would end up getting 6, but that is the wrong answer. Okay, because remember, the first thing I do with imaginary numbers is I pull out the I. So I'm going to write this as square root of negative 1, square root of 4, square root of 3. That's all the 12, right? And then the 3, square root of negative 3, is the square root of negative 1, square root of 3. So when I multiply it all out, notice what happens. I get an I. The square root of 4 is a 2. Okay. The square root of 3 times the other square root of 3 is going to just be 3. And this is another I. Okay. Now, we end up with 6I squared. So, we haven't talked about what I squared equals yet. If I is the square root of negative 1, and I square both sides, then I end up with I squared. When I square the radical, I end up with just the negative 1. So I squared is defined as negative 1. So now that I know that this I squared is negative 1, my answer simplifies to negative 6. Okay, so the correct answer is negative 6. The answer that we would have gotten if we had just multiplied them together without pulling out the i's would have been 6, and that would have been wrong. So every time we do anything with imaginary numbers, that's a negative under an even indexed root, then we're going to have to pull out the i's first before we start to apply our product rule, quotient rule, etc. All right, so on this one, I would actually get the right answer if I went ahead and multiplied them together, because I would get the square root of a negative 18, and then I would have to simplify that, and it would have an I in it, okay? Or I can go ahead and turn this one into an I, and I'd say square root of 3 times the square root of negative 1 is going to pull out, and then I'll just have the square root of 6, which is I square root of 18. And notice that this one will simplify to I square root of 18. But square root of 18 can simplify further. So we're going to break that up into the square root of 9, the square root of 2. And the square root of 9 becomes a 3, so 3 square root of 2. And then where will I tuck my I? Right before my radicals. So I would not put the I in front of the 3. It's 3I square root of 2 would be the final answer on that one. So now we're talking about adding and subtracting complex numbers. And this is very easy Because we've been adding like terms since you were in elementary school. If you were going to add fractions together, you had to add like denominators. Okay, when you got into algebra, you had to add like variable parts. Well, now, of course, real numbers and imaginary numbers are not like terms. But if I have two real numbers and I have two imaginary numbers, then they would be like with each other. Okay, so 7 plus 3 is 10. And my imaginary parts would be 5i plus 6i, or 11i. And this would be my correct answer. So when I'm adding, I simply add the two real parts together and the two imaginary parts together and put it in complex form. See, it's in my a plus bi, my real part, and my imaginary part. So now we have subtraction. All right, now anytime we're subtracting and we have parentheses, we should take that minus sign and distribute it through to each one. In fact, I can think of this as a -1. A -1 times 10 is a -10. A -1 times a 2i is a -2i. And then there is no reason for this parenthesis to be there at all. So now that I have gotten the signs, the correct signs everywhere, I'm going to take my two real parts, a +4 and a -10, and add them together. And I'm going to get a -6. And I'm going to take a -3i and a -2i and add them together to get a -5i. I have my real part and my imaginary part in standard complex form. And then we're going to talk about multiplying with i's. All right, we already have it in the I form, so we don't have to worry about that. When we multiply, this is a monomial times a binomial. We're going to distribute just like we always have. 7 times 4 is 28. 7 times a -11 is a -77. And there's my I. And there's nothing I can do to simplify that. So it is in its standard complex form. All right, so now we have some more multiplication. And we have -6 being distributed to 3 minus I. So -6 times 3 is a -18. And -6 times a -I is a +6i. And that is finished. Okay. Now down here we have a FOIL because we have a binomial times the binomial. And we're going to do first outside, inside, last. So 9 times a -2 is a -18. And outside is going to give me a 9 times a 3i, which will be a 27i. And the insides will be a -5i times a -2 will be a +10i. And the last will be a -15i squared. -15i squared. Okay? Now, the I squared, remember, is defined as a -1. I squared is always -1. So now we're going to change the I squared to a -1, which is going to make this -15 times a -1 into a +15. I'm going to take the +15 and add it to the -18 and get a -3. And then I'm going to get the 27i and add it to the 10i, always real with real and imaginary with imaginary. And I'm going to get a 37i. So I wind up getting -3 plus a 37i when I work that problem. So let me get the whole board on there. That was two different problems. All right, so now we are foiling again, but look at what we're foiling. 9 plus I, 9 minus I. Those are conjugates. When I foil them together, something cool happens. Just like when I foiled together radicals, I got rid of the radical. when I FOIL together complex conjugates, I will get rid of the imaginary numbers and my number will become real. Let's FOIL it. First is 81. Outside is negative 9i. Inside is positive 9i. And the last is negative I squared. Okay, but so this one, the negative 9i and the positive 9i, and we wind up with 81 minus I squared. But the I squared is a negative 1. So we wind up turning this into a negative 1. So we've got 81 minus a negative 1, which is 81 plus 1, which is 82. Okay, now remember when we were doing conjugates before, we did A plus B, A plus B, A minus B, and when we FOILed that together, we got A squared minus B squared. That's what we got when we were doing real math, okay? But notice what's going to happen here. Because this B is going to have an I squared in it, it's going to end up being because I'm going to put a little I here for conjugates, okay, then this is going to be an I squared, B squared, I squared, and the I squared is going to be negative, and I'm going to wind up with A squared plus B squared is going to be the formula that we will use for conjugates. So if I look at this one, when I multiply by its conjugate, which is negative 7 minus 2i, then I should expect to get A squared plus B squared. A is negative 7, so negative 7 squared would be 49. And then B is 2, so B squared is 4. I should expect to get 53. Okay, so let's do it. Let's FOIL it. Negative 7 times negative 7 is 49. And then the outside is a positive 14i. The inside is a negative 14i. And the last is a negative 4i squared. Okay, the 14i and the negative 14i cancel. 49 minus 4 times a negative 1 is a plus 4. 49 plus 4 is 53. So we have a little bit new, different formula than we had before. All right, so now, just like with radicals, now, can you see why they put imaginary numbers in the radical section? All right, all of chapter 9 was radicals. Well, because the square root of negative 1 is I. And also, one thing that's really cool is we do the same thing for imaginary numbers in the denominator as we do for radicals in the denominator. Remember, when we were dividing with radical numbers, we really didn't worry about dividing anything. We were rationalizing the denominator. We were getting the radical out of the denominator, which simply meant we were simplifying. Okay, so like radicals, we are not allowed to leave an I in the denominator. So we are going to get the denominator real. And that's what that's goal here. Okay, so now we're going to take what we just learned on the last board. When we multiply by a conjugate, we lose all of our imaginary parts. So we're going to multiply by 1 in the form of the conjugate of the denominator. 6 minus 3i, 6 minus 3i. And when we do that, the denominator is going to become a squared plus b squared, or 36 plus 9, and 36 plus 9 will be 45. In the denominator, we're going to distribute the 9 across. So 9 times 6 is 54, minus 9 times 3i is negative 27i. Okay, so 54 minus 27i over 45. Now, there's two things I have to do. Number one is these all have factors. I can divide all of them by 3. And I know I can divide them by 3 because remember my 3 rule is when I add the digits together and it's a multiple of 3, then the number's divisible by 3. So all of these are divisible by 3, so we're going to divide them all by 3. And 54 divided by 3 is going to be 18. And 27 divided by 3 is 9. And 45 divided by 3 is 15. Okay, so we don't have, well, we still have a 3. No, let's see. We have a 3 and a 3 and a 3. Okay, because this one is 3 cubed, and this one has a 6, and this one has 9 times, no, that's 9 times 5. Oh, but it does have 2 3s in it. Okay, so we're going to divide by 3 again. And we're going to get 6 minus 3i over 5. Okay? But I have to do one more thing. And that is always separate my real part and my imaginary part. So 6 over 5 minus 3i over 5. And now I have it in the proper form. And whether I put the I there or usually I stick it out to the side here. This is my proper form, okay? So when I'm doing this one, I am going to get rid of the I in the denominator. So I'm going to multiply by 4 plus 11i. 4 plus 11i. In the denominator, because I multiplied by conjugates, I should get a squared plus b squared, which is 4 squared, 16, plus 11 squared, 121. And that's going to be 1, okay, let's see, 6, that's 13, and carry my 1, so 3, 4, 143, check my math. Okay, on the numerator, I have to FOIL. So I'm going to have negative 3 times 4 is negative 12. Outside is negative 33i. Inside is 4i. And last is 11i squared. Okay, but the I squared is negative 1. So this is going to become a negative 11, and a negative 12 is going to be a negative 23. And then my negative 33i and my positive 4i is going to be a negative 29i all over 143. Okay, well, these are prime, so I'm going to assume, I don't know if anything that goes into that. So I'm just going to go ahead and split this up and leave it like that in its proper complex form. Okay. The last thing that we're going to do is talk about the sequence of the imaginary numbers. Okay, there is a really cool sequence that's going on here. Now, we already talked about I, and we talked about I squared being negative 1. If I take I squared, this little identity here, and I multiply it by I on both sides, then on the left side I'll get an I cubed, and I'll get a negative 1 times I over here, which is a negative I. Okay, so I cubed is negative I. And then if I take this identity here and I multiply both sides by I get an I fourth is negative I squared. And negative I squared is negative a negative 1, which is positive 1. All right, so then I take this identity, I to the fourth is 1, and I multiply both sides by I again, and I get I to the fifth is 1 times I is I. And I multiply both of these sides by I again, and I get I to the sixth is I squared, which is negative 1. And then I multiply both of these sides by I, and I get I to the seventh is negative I. And I multiply both of those sides by I again, and I get I to the eighth is negative I squared, which is positive 1. Okay, now notice what's happening. I, negative 1, negative I, 1. I, negative 1, negative I, 1. That sequence continues forever. So, notice a couple of cool things. if I have an I squared, an I to the 4th, an I to the 6th, an I to the 8th, an even powered I will get a real number. And that real number will be 1 or -1. It will be 1 if that power is a multiple of 4. It will be a -1 if it's even but not a multiple of 4. Okay? And notice that all of my odd powers remain imaginary. They all have I's in them. I to the 1, I to the 3, I to the 5, I to the 7. They're all imaginary. They keep their I's. Okay? Now, here the sequence starts over again. The first one in the new sequence is always I. Okay? So if you're right after a multiple of 4 power, you will be back at I again. And, of course, the other one will be a -I. So let's do I to the 12th. I to the 12th is even, so it will be either +1 or -1, but 12 is a multiple of 4, so it will be a +1. Okay, let's do I to the 22. I to the 22 is even, but not a multiple of 4, therefore it will be -1. Let's do I to the 15. I to the 15 is odd, so it's going to be imaginary. Now, I to the 16 is a multiple of 4. So it's going to be a -1 because it's the third one in the sequence. The next one, the next power will be 16. So it's going to be a -I. -I. And the last one is I to the 41. And I to the 41 is odd, but it's right after a multiple of 4. So it's going to be I, because it's the start of a new sequence. And it's a really cool pattern. And we are done with 9.8. And this is Mrs. A. God bless you. I found one boo-boo. And this 143 was a boo-boo. It should have been 137 I added incorrectly. Sorry about that. Make that correction.